Good. All right, so we are talking about the valence bond theory in last class. So I in slide number 7 in last class. So I start from here, slide number 7. Slide 7. So valence bond theory. So what is the valence bond theory? So if you want to bond the two atoms together, you need to first overlap the orbital of the two atoms. For example, this is a hydrogen, and hydrogen has one s orbital. So this is a nucleus here, and outside is a one s orbital, and if there is another hydrogen atom, and this hydrogen also has one nucleus in center, and this is one orbital. So if you want to bond these hydrogen together to form the S2 molecule, that is H bond H, so what you should do is you should overlap this orbital with this orbital. So bring them together, and just overlap like this, yeah, just like so. This one is orbital overlap with this one is orbital, and this guy has one electron pointing upward. This electron is this orbital has one electron pointing upward, and these two electrons now occupy this region here, the internuclear axis here, like this. Yeah. So in this orbital, this electron may be moving all around everywhere like that when we talk in chapter 7. And this electron may be moving everywhere inside this orbital, but in the molecule, when they form the molecule, this orbital sit mostly between these two nuclei here, and the finding of the electron is most likely is this region, not this region, not this region. Here, but here you could find electron everywhere. Makes sense? When the electron, when the two atoms bond by overlapping the two orbitals, those electrons come and sit in between those nucleus. Yeah, and the place where they occupy is the where the two orbitals overlap. So this is called valence bond theory. So that's one point. And overlapping, so orbital overlap to form the bond between the atoms. So I just show the orbitals, and they overlap and they form the bond here. Overlapping orbital hold two electrons of opposite spin. I just write here that these two overlapping orbital holding the two electrons, one pointing up and another pointing down. If you hear at this stage, they were just pointing one direction, but when they overlap and form the bond, they are pointing in opposite direction, but that is opposite spin. And this one electron is coming from this one orbital of one atom, and another electron is coming from the orbital of another atom. Now, the bonding electrons are localized with a higher probability of being found within the region of space between the bonding nuclei. So I told you, so these two electrons, the bonding electrons, these two electrons are found in between this space, not everywhere like that. Yeah, so that's what that is telling. The bonding electrons are localized with a higher probability of being found with the region of space between the bonding nuclei. Right here is those electrons can be found. Both electrons are simultaneously associated with the both nuclei. So these electrons are property of this atom, and these electrons are also the property of this atom. So these two are kind of simultaneously associated with the both nuclei. So they are not moving all the way this region, all the way to another region. Yeah. So they are kind of property, like the property of both the atoms. All right. So that's what it is saying. So there are some valence bond terminology in slide number 8. So number 1 is overlap. So what is overlap? Overlap means there are two orbitals. One is from one atom and one is from another atom, and they come there and forms the overlap each other like this. So this is from one atom, this is from another atom. So this is one orbital, this is another orbital. They come and combine, overlap each other. Yeah. So this is simple. So the main points, what's that? Overlap. Two orbitals existing in the same region of space. So kind of they stay in the same region, right? And lone pairs. So for example, if you make a bond, like this, you have, let's say, you have maybe I just, so this is one orbital, this is another orbital, so there may be one orbital, there may be one orbital, so this is one orbital, this is one orbital, right? So this is from one atom, this is from another atom. So let's say this is carbon atom, this is carbon atom. So if this one is, if you see here, this is overlapping with this one, right? So these two are overlapping. So if the electron are sitting right here like this is called bond pair. Yeah. But if the electrons are sitting like this here, non-overlapping orbital, this is called lone pair. If the electrons are sitting in the non-overlapping orbital, this is called lone pair, LONE lone pair. And if the electrons are sitting in the overlapping orbital here, so they are called the bond pair, like this. This is bond pair. Then central atom. So central atom is if you have a three atom like this. So let's say boron is combined with the three hydrogen like this, hydrogen. So this is called central. Boron is called central atom. Yeah. So if carbon is combined with the two oxygen like this, so this carbon is called the central atom. Yeah, central. The atom of the atom of concern in the molecule, whatever, the center in the molecule. So this is the atom in the center of the molecule. Yeah, I don't know what that means here. The atom of concern in the molecule. So probably we'll talk later. So most of the time we will be talking about the central atom. And hybridization. So what is hybridization? So this is one important concept. So hybridization. So hybridization is like just how we hybrid the animal. Hybridization. So let's say this is one kind of dog, and another is another kind of dog. So we have two kind of dog here, and then we cross these two dogs together, right? And then we get, if we cross these two dogs together, we will find a next different type of dog, right? So different type of dog. It's not neither this dog, neither this dog. So this is a different kind of dog. So this is called the hybridization, right? So how we define the hybridization in animal kingdom? That's exactly same as the hybridization in chemistry. So for example, let's say, so hybridization. Let's hybridize some orbital. So what is the shape of this orbital? This is spherical, right? One is orbital. If you see here, this is one is orbital, spherical. Now, if you want to hybridize this orbital with this one, hybridizing means mixing. So this is a p orbital. Let's say this is a py orbital. So one s and one s, and you have a one p orbital. So this is a s orbital. This is a p orbital. Now you want to mix them together, and you want to produce third kind of the orbital. Make sense? So that's called the hybridization. So if you mix one s orbital with one p orbital, it gives the orbital like this. So something like this, you see here. So it's a hybrid orbital. So I mix s orbital with the p orbital. Now I produce this kind of the orbital. This is neither look like s, not look like p. It looks like different, right? So this is called the hybrid orbital. Make sense? So it's pretty simple. So you are mixing two kind of. This is a spherical, like a ball, and this is like a dumbbell. And if you mix a sphere with the dumbbell together and find the new type of the orbital, this looks like this. So this looks like a dumbbell, and there is a small, tiny two lobes there. So this is called the hybrid orbital. So basically, hybridization of the orbital means you are mixing two different type of orbital, and when you mix two different type of orbital, you will get third, a completely new type of the orbital. That's called the hybridization. So this is, and then the name of this one is called sp orbital. You see here, one s and one p. So that is called the sp orbital. Yeah. So for example, if you mix one s with the, let's say you mix with the s orbital with, let's say, two p orbital. So this is py orbital, and there is a, let's say, another orbital. So this is a this is a py orbital, this is a px orbital. Now I want to mix these three together, and what kind of the orbital I would get, right? So that hybrid orbital would be like this. So so this would be looking like this, yeah. So So you see, I just mix 3 orbital. One is a sphere and 2 dumbbell, and I got third type of the orbital. Looks like a flower, right? Just mixing. Don't think too much. So you are just mixing 2 different kind of thing or 3 different kind of thing, and you are completely producing new kind of thing. It's a hybrid, right? So hybridization is just exactly like how you hybrid the 2 kind of dog to produce third kind of dog. So this is called how many orbital I mix here? 1 s orbital and 2 p orbital. So I would write this as a sp2 orbital. This the name of this guy is sp2 orbital. Make sense? Why sp2? Because I mix 1 s and 2 p. So since p are 2, so this is sp2 orbital. Now how many is the number of sp2 orbital? This is 1 sp2. This is another sp2. This is another sp2. So how many sp2 orbital are there? So 1, 2, 3 sp2 orbital. Make sense? Easy, right? That's it. So this is a p orbital. This is s orbital. This is p orbital. This is p orbital. But when I mix, I put them in a box and mix together, and we get this kind of the orbital. And each one is named as sp2. So we have 3 sp2 orbitals. Yeah. So if you look the angle between these one, this is 120 degree. 120, 120 degree, 120 degree. Like a boron trifluoride or BS3, we'll discuss those molecules later. Yeah, but previously when I mix this s orbital with just a p orbital, with just a p orbital, I give you like this. So this is 180 degree. This is a linear orbital. So this is a linear bonding also. So like this. So how many sp orbital we have? I have this is s orbital, this is p orbital. 1, 2 orbital I am mixing. So how many orbital I was producing here? This is 1 sp orbital, this is another sp orbital. So we have 2 sp orbital. But in case of sp2 orbital, how many? So I am 1, 2, 3. I am mixing 3 together. So I am producing sp2, 3 orbital. So how many I start with? That many orbital I have at the product. Make sense? Easy, right? Now let's talk about another hybridization. So this is called sp hybridization. This is called sp2 because I take 1 and 2 p's. Now I'm going to talk about the third orbital. So third orbital. Now third orbital is let's say this is s orbital. Now I have 3 p orbitals. So this is a px orbital. This is px. Now I have another. This is py. Now I have another. This is pz orbital. So I have 3 kind of p orbital, right? Px, py, and pz. Now if I mix them together, I would get something like this. So here it exactly look like the CH4. So if you remember the CH4 molecule previously, I was telling you C is here, 1H is here, 1H is here, and there is a 1H going away from this board, and 1H is coming toward the board, right? CH4, something like that. If you remember that, the tetrahedral molecule. So it exactly look like that. So I'm mixing S and 1S and 3p orbital. So it looks like this. So this is one. So exactly. So this one is that one, and this one is coming toward me. So this one is coming toward me here. So this one is coming toward me. This one is maybe in the plane of the board, and here. So this is this one, and this one is this one, and this one is going away from this board. So something like this, exactly like the CH4 molecule. So how many orbital I get here? So I mix 1 s orbital with a 3 p orbital, and I get 1, 2, 3, 4 orbital here. So the name of this guy is sp3. So the name of this guy is sp3. Now name of this guy is sp3. Name of this guy is sp3. So I have 4 sp orbital. Why? 1, 2, 3, 4. I mix 4 things, and I produce 4 hybrids. Make sense? So that's a sp-q orbital. And if you measure the bond angle between these orbitals, 109.5 degree. 109.5 degree. 109.5 degree. 109.5 degree. So this is called the hybridization. So how many kinds of hybridization we study in this course? 3 kinds. One is sp, another is sp2, another is sp3. So you just finish this one, and this is hybridization. So this is the most important concept we wanted to study here. So if you mix one S and one P, you will produce two sp hybrid, and the number of this is 2. And if you measure the bond angle between them, the angle between this sp hybrid orbital, so this is 180 degrees. So it's a linear. So how many sp orbital we do? We produce 2. This is sp, this is sp. And if you measure the bond angle between these two sp, we have 180. And then if you mix one S with the 2P like this, PXPY, and you would produce SP2. So this is how many orbital I would get? 3 orbital I would get. And they are exactly look like the boron tribe 100. Yes. I need to put them in equal distance actually, like this. So this is sp2, this is sp2, this is sp2, and the bond angle will be 120 degree, 120 degree, and 120 degree, like this. And then if I am mixing 4 orbital, same thing that I told previously. This is sp3 orbital we get, and if I make the so this is I have 4, so 4 sp. So this is 2, this is 3. This is 3, this is 4. Now this is like this. So this one is that, and this one is that, and this one is going away from the board, and this one is coming toward me, So if you measure the bond angle, 109.5. sp3, 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 like this. Yeah. So this is called the hybridization. So if you understand this much, all bonding valence bond theory is that much. Yeah. Then hybrid orbital is that one, and sigma bond. Now let's talk about the sigma bond. I already told you in the previous class, if there is a head-to-head collision, that's called the sigma bond. So let's say, so this is a p orbital, some kind of the p orbital, and this may be s orbital. So it's a kind of the head-to-head collision, and this kind of the head-to-head overlap give you sigma orbital, sigma bond. So this kind of bond is called sigma bond. But if there is a one orbital like this, and there is another orbital like this, and let's say you have one electron here, and they overlap. So these two guys overlap. So these two guys overlap, and electron sit here. This is called pi bond. This is called pi bond. Yeah. So if the head-to-head, if two orbital are overlapping head-to-head, it is called sigma. If they are overlapping sidewise and the electron sit there, that's called the pi bond. Yeah. It's called the pi bond. Now, single bond and double bond. Now let's talk about the single bond and double bond. So let's say we have something like this. So this is a s orbital. This is s orbital. So they are head-to-head overlapping. So if the bond forms by like this way, that is called the sigma orbital. Head-to-head, right? Sigma bond. Now how about the pi bond? So pi bond is a double bond. So pi like this. So let's say we have a orbital like this. So this one is this one, and this one, something like this, and another atom has a so this is one atom, orbital from one atom. So another atom has orbital exactly like that, like this, right? Now it's actually they are of the same size, like this, and the you see here, this guy and this guy are overlapping head to head. So this is a sigma bond here. This is a sigma bond, and this guy and this guy may be overlapping each other. And if they overlap each other, they form a region here of overlap, and this region is called the pi bond. So pi bond is above the sigma bond or below the sigma bond. So this is a double bond. Make sense? This is a, so if you look carbon, so this looks like this. So this guy, this two electron, this bond is sigma bond. It's forming from the head-to-head overlap. But this another bond is from this one. So one p and another p orbital are just two kind of orbital are two orbital are overlapping here and giving this bond. This is up above the plane of this internuclear axis. Yeah, one is above, and if there are three kind of the orbital, so let's say I have another orbital here. Let's say I put another orbital here like this, because we have three kind of p orbitals, right? So I have here another one like this, and let's say there is an overlap between, there is one electron, there is one electron. So if this guy overlap with this one and form the bond here, that's called another bond, and that is C. So this one is a sigma bond from head-to-head overlap, and this one is coming from the overlap of this py and py, and this bond is coming from the overlap of the pz and pz kind of thing. So like this, yeah. Make sense? Because we have three kind of the p orbital, px, py, and pz, right? So if px and px, so this is a px, this is a px, so they come like this and form a bond here. That's called a sigma bond. And this is a py orbital going up, this is a py orbital going up. They just come like this here and form a space somewhere, and the electron occupy this region. That's called the pi bond, right? And there is a pz orbital like this. So pz is pointing like this, pz is pointing like this. And they also come together near, and then they just make up some space where they can share the electron, and that's called the pz. Make sense? So the pi bond. So pi bond can be two kinds. Good. Alrighty. So pi bond either is coming from the py to py overlap or pz to pz overlap. Let's talk more here. So that's a double bond and triple bond. We just finished this one. So in slide number 9, I'm writing exactly the same thing. So let's look here, some hybridization here. So this is a sp2 orbital. So if you look the slide number 9, so we have the sp2 orbital. So carbon has if you look the carbon electronic structure, 1s2, 2s2, 2p3, something like this. So one is they don't take part in the reaction. So inner electron we don't consider. So we have 2s2 and 2p2. So what we do is we mix some orbitals. So this is a sp2. So what we would mix this s orbital, which is spherical, and that there are 3p orbitals. You see the 2p are like these three boxes: px, py, pz. So we have three axes. So sorry, three orbital here. But if you look the structure of this one, so px looks like this, py looks like this, pz looks like this, right? So we have three kind of this orbital. So in this one, we are just making the sp2 orbital. So we are mixing s with the px, and this is a px, then this is a py. So if you mix sp and x, spx, and py, you would get a hybrid orbital of like this. So you have 1, 2, 3. So this is should be in the same plane. So this is 1, this 1, 2, 3. So I just want to. So it looks like this, like the boron is in the same plane. So this is a paper. So one of these orbital is in this end, one of these orbital is maybe somewhere in between, and one of these orbital is somewhere here. So in the same plane, yeah. This is called sp2 orbital. This is sp2 orbital of one carbon atom, and this is sp2 orbital, right? Now maybe I just put this a little bit different way just to make a. So kind of still a little bit hard to draw. So something like this. This is sp2. So if you look at the bond angle of 120, 120, 120. So this is from one carbon. So where is the another orbital here? So carbon has CS, px, py, and pz. I have not write the pz yet. So I have a px. I write the py, but this pz I have not taken into consideration yet, right? So this one is this guy. So this guy, you see here, this one going up and down is a pz, but this one is sp2. This one is sp2. This one is sp2. This one is sp2. Make sense? The pz orbital did not hybridize, so pz just stays there, doing nothing. Make sense? So there are there are 4 orbitals with the carbon in the valence shell. So one 2s and 3 2p. So this is 1 This is 2s and 2p, 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 and this guy, and this guy mix together and give this sp2, sp2, sp2. But this pz don't mix and just hanging there just as it is. So that didn't hybridize. Did I make it clear? Good. Now this is from one carbon. Now write from another carbon. Exactly same thing. So another carbon has something like this. So another is hanging like this, up and down like this, yeah? Like this. So from another carbon, this is sp2, this is sp2, this is sp2, and this is pz, this is pz, this is unhybridized. So this guy and this guy, you see that these two lobes, they are not hybridized. And if you look here, this sp2 and sp2 overlap each other and form a bond. So this is a sigma bond. So if you look at the two carbon atom here, so this is one carbon, this is one carbon. So here is one bond. So this is called sigma bond. So this is called sigma bond here. So this guy right here is a sigma bond, right? Now what happened here is this one and this one overlap. Now this pz and pz, which did not hybridize. You see, this is hanging down up, and then this one and this one just come near and they overlap each other here, and they form the this bond, another bond here. That's a pi bond. Make sense? Pi bond. So this guy is pi bond, this guy is sigma bond. Now where is this sp2? So sp2, this guy is just pointing here this way, this guy is pointing this way, and this sp2 is pointing this way, and this guy is pointing this way, like this. Like this, yeah? So like this. And what happens is the hydrogen, if you have a hydrogen somewhere here, one is orbital. So this hydrogen one is orbital come in overlap here, hydrogen one is come in overlap here, hydrogen one is come in overlap here, and hydrogen one is comes in overlap here. So this molecule is CH2CH2. So this comes like this, C, double bond C, and then this is H, this is H, this is H, this is H, like this. Make sense? Now, I already told you what is the bond angle between this sp2 and this sp2, 120. So this angle is 120. What is the bond angle between this guy and this guy? 120. So it's a 120. And what is the bond angle between this guy and this guy, sp2, sp2? 120. 120. So what is the bond angle here? 120, 120, 120. It's like that, yeah? So if you will write the bond angle here, so see, three-way pointing. One this way, one this way, one this three-way pointing. 120, 120, 120, 120, 120. All bond angle are 120. If anybody is writing any message here, let me see. How did you find the pi bond? How did I find the pi bond? So pi bond, what I did is like this one. So sp2, sp2. First of all, I mix three. This s, p, p. So only these three. 1, 2, 3. These three I mix together, and I produce sp2, sp2, sp2 in one carbon atom. I did the same thing in another carbon atom. I find sp2, sp2, sp2 here, and one I didn't mix it. So this guy is not mixing with other. So this is just hanging up and down. This is hanging up and down. And this guy and this guy just come together and overlap with each other, and they have one electron, and this have one electron, this and one electron, and they sit here by pairing. So that's the pi bond. Make sense? So that was the question here. How did you find the pi bond? Good. So the most important thing, when you see something like this, so something here and pointing three-way, and there are no dot electron, always 120 degrees. So this is 120 degrees, sp2 type. Yeah? Good. Now, okay. So what is hybridization? I already told about the hybridization. Hybridization, the atomic orbital combine to give the new type of the orbital, and that can be used to model the atom molecules and molecular geometry. Now let's go to slide number 11. So this is the sp2. I just discussed is the sp2 kind of hybridization. Now let's talk about the sp3 type. So same thing, I already discussed it. So I have the three kind of the py orbital. So this is the s orbital. Again in the carbon, we are talking in the carbon. Carbon, if you look the carbon, 1s2, 2s2, 2p2, 2p2. So this is the electronic configuration of carbon. I don't need inner this one. I just need this 2s and 3 2p orbital. So this is, I'm just working with the one carbon. So this is the s orbital. This guy 2s, and then I need sp3. So I have a px. So this is a px orbital. Now I have a py orbital. This is a py orbital, and I have pz orbital. So this is pz orbital. So this is a little bit, it's very hard to write the pz orbital in board, right? So it's basically like this. So I can show you. So it's like this. So this is a px, yeah. This is a, so this is a px. So I'm holding like this. This is a px, and this is going up and down like this. This is a py, and this guy is coming toward you and me. So this is pz. So this guy is a pz. It's like this, yeah. So in board it's hard to write. So we just write this like a slanting, but it is not slanting. It is like this. So this one is a px. This is east and west is px. Up to ceiling and down to earth is this py, and this guy is a pz. One is coming toward you, one lobe is coming toward you, and one lobe is coming toward me. This is pz. So it's very hard to write in board, so we write that is a slanting, but it's not a slanting like this. It's just like here, 90 degree, and it's coming toward you and me. Make sense? Good. So that's a pz. So these three kind of the orbital here. Now mix these three together. So it's very easy. So mix them 4 orbital together. If you mix a 4 orbital together, what happens is like this. So this is like this, this is like this, and this is like this, and this is like this. So this one is going away from the board. This is coming toward us, and then this one is on the plane of the board. This is a sp3 orbital. So 1, 2, 3, 4 sp3 orbital. So if you want to make the model of this one, it looks like this. So this looks like this. So if I hold this one like this, so like this and like this. You see here? Make sense? So this one is in the plane of this board. This one is also in the plane of this board. This is trying to penetrate this board and going away, and this is coming toward you. Make sense? So this is the sp3 orbital. So this one is this guy. This lobe is this one, and this guy is this one, and this guy is this one, and this the point penetrating. This is trying to go away by penetrating this board is this one. Make sense? So this is the sp q orbital. How many sp-q orbital I have here? 1, 2, 3, 4. Now bring a hydrogen here. So I have a, this is from the carbon. In center is the carbon. So this is the hydrogen. So bring the hydrogen and put it here. So the head-on overlap. So this is the hydrogen carbon, one hydrogen and carbon bond. And bring another hydrogen and put here, head-to-head overlap. That's another CS bond. Bring another hydrogen and put it here, head-to-head overlap. That's another carbon hydrogen bond. And bring another hydrogen and put it here, and that's another hydrogen. Make sense? So the bond angle is 109.5. So the bond angle here is, so this is one sp-q, this is another sp3. You can call sp-q or sp3. This is sp3. This is sp3 of carbon. Now you have 4 hydrogen. Bring one hydrogen. Hydrogen has something like this s orbital. So bring it here and overlap it here. So this is hydrogen, one is hydrogen orbital. So here you form a 1 sigma bond. Bring another hydrogen from here, make a bond here. This is hydrogen. So bring another hydrogen here, make one bond here. Bring another hydrogen here and make one bond here. You see here, this is the CS4 molecule. Make sense? So one s orbital of hydrogen is overlapping with sp3 hybrid orbital of the carbon and making the CS4 bond. It's like that. So if you want to draw it here, so I can draw it. So like this. So this is C, that's the central C, and then this is this bond is representing this one, and this one is representing this one, and then this one is going away, trying to go away there, and this one is coming toward you like this. And if you look the bond angle, 109.5, 109.5, 109.5. How did we get the 109.5? Because they hybridize and give a sp3 hybrid orbital, and sp3 hybrid orbital have 109.5 degree bond angle between them. Make sense? Like this. If they didn't hybridize, the orbital would look like this. So this is the px orbital, and this is a py orbital, and then this one coming toward is a pz orbital, and then the bond angle for the CS4 would look like the 90, 90, 90. So the angle would be 90 here, 90 here, 90 here, and this between this and this is 90. So bond angle become 109.5 instead of 90 because of the hybridization of the orbital of the carbon. Make sense? So just like this. So I just finished the expected molecule was 90, but actually it's a 109.5 due to the hybridization. So CH4, I already told you in chapter number 4, if you see the 4 bond around the pointing 4 way, that's a tetrahedral, the angle is always 109.5 due to the hybridization of the orbital. Good. Now let's look I just finished this one. One thing I want to talk a little bit in the chapter, slide number 12. Slide number 12. So if you look here, so so we have a 1s2, 2s2, 2p2 in carbon, right? So nucleus is here. So the energy of this electron is very, very small because they are very near to the nucleus. But again, we don't use this one. And if you look here, the energy of 2s is small. So the energy is small because they are in the short distance from the nucleus. The energy of this p is high. The energy of the p orbital is high. Orbital is high. You see? So energy of this one is low. Energy of this one is high, right? Now, if you mix this together, all will have same energy. Make sense? So if you mix this S and P2, so somewhere there energy would be SPQ. So from here, so their energy is somewhere in between this one. Make sense? So energy of S is very small. Energy of P is very high. But once you hybridize this to one, the energy of these two orbital, the hybrid orbital becomes in between S and P. Make sense? So like that. So I can write it. I wrote here is a box form. Now let's see. Let's see here. So when two s orbital. So this is S and this is P. 1, 2, 3. So this is 2s orbital. 2s orbital have 2 electrons. P orbital have 2 electrons. So this is Px. This is Py, and this is Pz. Pz don't have the orbital there. So energy is low. This energy is low. Because somewhere here is the nucleus, and from nucleus this electron are near, so the energy is low here. So energy of this is high. Energy is high. Yeah, in unhybridized case. Now let's hybridize it, and once you mix these 3 together, so just put in a box and mix them together, and all will have same energy. So they will all have same energy. So this will have SP. Let's say this is one SP, another SP, another SP, SP3. So this is also all same. This is so SP, 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 SP. So all are of same size. So energy will be, so 1, 2, 3, 4. So now we start 1, 2, 3, 4, like this. So again, the electrons should be filled according to the Hund's rule, 1 by 1 first, and then 1 after that. Yeah, in the hybrid. Make sense? Like this. See? So here, this has a low electron energy. So I was low energy. So I was putting 2 here because it is a low energy orbital, and I was putting 1, 1 here. So this is a high energy condition. Now I mix these 2 together, and both the energy of our hybrid orbital energy will be somewhere here. This is low, this is high, and then our hybrid orbital energy would be something like this. And since all of these orbital have same energy, I need to put the electron according to the Hund's rule, because I have 1, 2, 3, 4. So I should put 1 by 1. Previously it is different, so I put 2 here. It's different, so I put 1, 1 here. Now this one all are same. Now I need to put 1 by 1 the electron. Make sense? Good. So that's like that. Good. So So another way, if you look in that slide number 13, another way of writing this one, I'm just writing the different way, the same thing, but I'm trying to explain the same thing the different way, yeah, so that you don't get confused when you look the book. So if you look another way, so 2s is this one. So this is a 2s orbital. There are 2 electrons. And is a p orbital. So this is p orbital. So this is px, this is py, this is pz. So one electron here, like this in carbon. Now mix this, put in one box and put together and mix them. And when you mix them, you produce a 4 hybrid orbital, sp3. So this is 1s, this is 1, 2, 3. So sp3. So these all are sp3. So this is sp3, this is sp3, this is sp3, this is sp3. So I have 4 sp3 here. Sp3 here. So you see here, maybe I need to put a really low here. This is 2s here. Really low energy, really high energy, high energy. So if this energy is going up, this energy, energy, energy. So high energy, low energy. After mixing and producing hybrid orbital, the energy of hybrid orbital is above this 2s orbital, and then below this p orbital, somewhere in between. Make sense? Just saying the same thing the different way. And then if you put the electron 1, 2, 3, 4, so 1, 1, 1, 1. You need to put like this. Make sense? Simple. Now, if you are combined, so this is from the C. So if this is from the C. Now let's say you have a 4 hydrogen atom here. 1, 2, 3, 4 hydrogen atom here. So it has 1 electron, 1 electron, 1 electron, 1 electron. So one guy of this hydrogen come and combine here. So this electron is coming from hydrogen. This one coming and sitting from hydrogen. This is coming from and sitting with hydrogen. This is from hydrogen. So it comes like the CH4. So now once you put this electron from the hydrogen, this becomes the CH4 molecule. Make sense? Good. So first you hybridize, and after hybridize, you make the bond. Yeah? Good. How about CS4, CH4? Now I'm going to draw another. So I already did the CS4. Now I'm going to draw another molecule here. So let's see this one. Now let's explain the bonding in this molecule. C, H, 1, 2, 3, 4, right? 1, 2, 2, 3, 4, like this. So how do they bond? Let's explain the bonding in this molecule. Exactly as CH4. This is a tetrahedral molecule. So this is a C. Let's write the hybridization of this C. C is connected with 1, 2, 3, 4 tetrahedral, 4 side, 109.5 bond. 109.5, 109.5, 109.5. So this is a sp3 hybrid orbital. So this is sp3, and this is 109.5 tetrahedral. Carbon is pointing 4-way, 1, 2, 3, 4-way bonds. So this is also 109.5, 109.5, 109.5. This is also 109.5. So this is also sp3 hybrid orbital. Now let's draw this one. So hybrid orbital of this carbon is like this. So this is one. This is this one, and this one, and this one. So this is going away from you. This is coming toward you, and this is in the place of the board. And there is another carbon here. So exactly same. So one is going like this. This is sp3, and then this is coming in here. This is another here, and this is another here. So this one and this one are overlapping here. You see? So this one. So this is sp3, 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 sp3 of another carbon. This is sp3, 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 sp3 of another carbon. So this one and this one are the two sp3 are doing head and overlap, right? The head of this one is coming here and overlapping and giving the sigma bond here like this. And then so this is this one, CC bond, C and C bond. Now carbon, one hydrogen come here and sit here. So this is another hydrogen come here and sit here. Hydrogen one is come in overlap and make that one. Same thing here, same thing here, same thing here. So this is like this. Make sense? You just need some practice, yeah? So if something has a tetrahedral structure, immediately, so like this one is, I just hold it here. So like this. Like this. This is this lobe, this is this lobe, this is going away from you and pointing away from the board, and this is coming toward you. Yeah, tetrahedral. Tetrahedral bone angle is always 109.5. Yeah? Good. Now, so I just finished this one. So they may be showing you small lobe here. So actually SPQ looks like there are small lobe after SPQ is formed. So you don't have to worry to show this small lobe there. Yeah, just show these big ones if you need to draw. Now let's look some example here. I still have 5-minute time. So once we know this one, then other thing will be very easy. So why CH4 bone angle is not 90 but 109.85? Because of the hybridization of the orbital. Yeah. So meaning that I was telling you. So in board actually we write like this S. So it looks like a 90 here, but this is not true. This actually is like this, H, and then this one is going away from you, and this one is coming. So this is the real molecule. It is due to the hybridization. Yeah. Hybridization. Now look at the slide number 15 in NS3. So let's look at the NS3. So you have a N. N is 7. So if you look the electronic configuration, that's 1s2, 2s2, 2p3. So this is the nitrogen, right? So inner orbital don't take part in the electron. The bonding. Now we need to do the this one. So if you look the nitrogen molecule, it looks like this. Nitrogen. This is nitrogen. This is hydrogen. This is hydrogen. This is hydrogen, and there are 2 electrons here, like this. These 2 electrons here. So if you look the electron pair geometry, how many electrons are here? How many directions? This is one direction. This is another direction 2. This is another third. This is another 4th direction. So this is also a tetrahedral geometry. Make sense? But why it looks a pyramid is because the valence bond electron pair theory, repulsion theory, they are repelling these electrons more, and it looks like a pyramid. So how can we explain this bonding here? So again, you see here, so this is 2s, this is 2s. There are 2 electrons. Now there are how many? 1, 2, 3 boxes here. So 1, 2, 3, like this. So this is 2s, this is 2p. Make sense? 3 electrons. Now the electron of this guy is small. The electron of this guy is the energy of this guy is small. The energy of this guy is more. But now if you hybridize this, the energy becomes somewhere in between, right? Now you need to hybridize it. So if you want to draw something like this, it's okay. So this is 2s, this is 2p, 1, 2, 3, 2p. This is 2s, this is 2p. Now I want to mix these two together and hybridize them. When I hybridize them, it becomes SPQ. So S, P1, P2, P3, 1, 2, 3. Sorry, 1, 2, 3, same side. So I have 1, 2, 3, 4, 5 electrons. Now I start to put this electron here. So after hybridization, so this is the S, this is the P. Now this is sp3. Now I put the electron 1, 2, 3, 4, 5. First I need to put one by one. 1, 1, 1. Now I put sp3. No, sp3 is 4 orbitals. 1, 2, 3, 4. I need to have 4 orbitals here, not 3. sp3, right? I'm mixing 1, 2, 3, 4. So I have 4 boxes here. 1, 2, 3, 4. Now I need to put one by one first. 1, 2, 3, 4, 5 electrons. 1 electron, 2, 3, 4 electrons. Now I have one more electron here. 5. 1, 2, 3, 4, 5. Now I have 4 already filled here. Now I put 1 here. Now this is all are sp3 orbitals. This is sp3, sp3, sp3. 4 sp3 orbitals. Make sense? Now, how do I draw this sp3 orbital? Again, the same thing. sp3 orbital are pointing to like this. So here, one is pointing this way, one is pointing this way, one is pointing this way, one is pointing this way. This is sp3 orbital, right? 4 sp3 orbital. Make sense? 1, 2, 3, 4. And I told you this is maybe this is in the plane, this is in the plane, this is coming toward you, and this is going away from the board, right? sp3. Now one hydrogen come here and sit here, one hydrogen come here and sit here, one hydrogen come and sit here. So here, one hydrogen come and sit here, hydrogen come and sit here, one hydrogen come and sit here, like this. But this 2 electron sit right here is a lone pair, like this. Make sense? So this is H, and this is H, and this lone pair are pushing this bond pair down, so this structure becomes the pair meter. I think we stop here. Hopefully you understood something. Just repeat it, yeah? Thank you, everyone. I'm going to stop it here.